Welcome to this coding tutorial. Today, we'll be exploring problem number 671, titled Second Minimum Node in a Binary Tree. In this problem, we'll dive into an interesting binary tree scenario where the goal is to identify the second smallest value among the unique node values. It's a great exercise for practicing tree traversal and problem-solving skills. Let's get started. In this problem, you are given a binary tree that has a special structure. Every node in this tree either has 0 children, meaning it's a leaf node, or exactly 2 children. Additionally, the value of each node is guaranteed to not be greater than the values of its children. Your goal is to find the second smallest value in the tree. If no such value exists, the output should be -1. A crucial property of this tree is that the root node always contains the smallest value in the entire tree. You'll be provided with the root of the tree as the input, and the output should be the second smallest value as an integer. If there is no second smallest value, you'll simply return -1. Take a look at the first example. The tree's root node has a value of 2, and its 2 children are 2 and 5. The right child, which has a value of 5, also has 2 children, 5 and 7. In this tree, the smallest value is 2, which is at the root. To find the second smallest value, we look for the next smallest number greater than 2. Here, that value is 5, so the output for this example is 5. Now consider another example, where the tree has all its nodes with the same value. The root and both its children have the value 2. Since there is no value greater than 2 in the entire tree, the second smallest value does not exist, and the output is -1. Now, here's one more example. The root of the tree holds the value 1, and its 2 children have the values 1 and 3. The root's value, 1, is the smallest in the tree. To find the second smallest value, we need to identify the next smallest number greater than 1. In this case, the value 3 is the next smallest. Therefore, the output for this example is 3. This demonstrates how the tree structure and the values of the nodes determine whether a second smallest value exists, and if it does, what that value will be. To summarize, the problem has a few constraints and edge cases to consider. The tree will always have between 1 and 25 nodes, and each node's value will be an integer between 1 and 2 to the power of 31 minus 1. A key edge case is when the tree has only one node. In that situation, there is no second smallest value, so you would return -1. Similarly, if all nodes in the tree have the same value, the second smallest value does not exist, and the output is -1. On the other hand, even a small tree with just 3 nodes can have a valid second smallest value if the children of the root have different values. For instance, if the root value is 1 and one of the children has a value of 2, the output would be 2. By keeping these constraints and edge cases in mind, you can approach the problem effectively and handle all possible scenarios. To begin, let's consider the brute force approach, which relies on an exhaustive search to find the second minimum value. The intuition here is straightforward. We can traverse the binary tree to gather all the unique node values, store them in a set to eliminate duplicates, and then sort the set to identify the second smallest value. The steps involve performing a tree traversal using either DFS or BFS, adding each node's value to a set, and then sorting the set to access the second smallest element. If no second smallest value exists, we simply return -1. While this approach is simple to understand and implement, its inefficiency becomes clear when we analyze the complexity. The sorting step introduces a time complexity of O, n log n, and the space complexity is O, n, due to the storage of unique values. This method fails to take advantage of the tree's inherent structure, leading to unnecessary overhead in both time and space. Now, we turn to a more efficient solution, the optimized approach using 2 minimum tracking. This method leverages the special properties of the tree, where each node's value is not greater than its children. With this in mind, we observe that the smallest value in the tree is always the root value, and the second smallest value, if it exists, must be located in one of the root subtrees and must be greater than the root value. By skipping subtrees where all values are the same as the root, we can eliminate unnecessary exploration. The steps involve initializing the smallest value as the root's value, then traversing the tree recursively. During traversal, if a node's value is greater than the root, we consider it as a candidate for the second smallest value. Otherwise, we continue exploring its children. By tracking the smallest value greater than the root throughout the traversal, we can efficiently identify the second smallest value or determine that it doesn't exist. This approach has a time complexity of O(n), since each node is visited once, and a space complexity of O(h), where h is the tree's height due to the recursion stack. It's a significant improvement over the brute force method because it takes full advantage of the tree's structure. An alternative method to the optimized approach is using an iterative BFS. The intuition here is similar, but instead of recursion, we use a queue to perform a level-order traversal. During the BFS, we keep track of the smallest and second smallest values encountered. Nodes with values equal to the root are skipped, and we update the second smallest candidate as needed. Once the traversal is complete, we return the second smallest value or -1 if no valid candidate exists. This method has the same time complexity of O(n) as the optimized DFS, but its space complexity is O(w), where W is the maximum width of the tree. While BFS can be more memory intensive for wide trees, it avoids recursion and provides an alternative way to solve the problem efficiently. The choice between DFS and BFS often depends on the specific constraints of the tree and the programmer's preference. After evaluating the various approaches, the optimized DFS strategy stands out as the most efficient and practical choice for this problem. By skipping unnecessary subtrees and directly tracking the second smallest value, it minimizes computational overhead while remaining straightforward to implement. Unlike the brute force approach, it avoids the costly sorting step and leverages the tree's structure to reduce the work required. While BFS is a viable alternative with similar time complexity, DFS typically has lower space usage in the case of balanced or deep trees, making it a better fit in most scenarios. One trade-off to note is that DFS recursion depends on the tree's height, which could lead to stack overflow in extremely deep trees. However, given the problem's constraints, this is rarely a concern in practice. Ultimately, this strategy achieves a time complexity of O(n) and a space complexity of O(h), ensuring that we can solve the problem efficiently without unnecessary computations or memory usage. In this problem, we need to find the second smallest value in a binary tree. It's important to note that the tree can contain duplicate values and is not necessarily a binary search tree. If there's no second smallest value, for example, if all the nodes in the tree have the same value, the algorithm should return -1. To solve this, we start by taking the root node of the binary tree as input and aim to output either the second smallest value or -1. The steps of the algorithm involve initializing data structures, such as a set to store unique values and a queue or stack for tree traversal. We use these to perform either a breadth-first search, BFS, or depth-first search, DFS, to traverse every node in the tree. Let's discuss these steps in more detail. As we traverse the tree, we add the value of each visited node to our set of unique values. This ensures that duplicates are automatically filtered out. Additionally, for BFS, we enqueue the left and right child nodes of each visited node, or for DFS, we push these nodes onto the stack, ensuring all nodes are eventually processed. While traversing, we handle edge cases, such as an empty tree. If the root node is null, we can directly return -1 since there are no nodes to evaluate. Similarly, after completing the traversal, if our set of unique values contains fewer than 2 elements, we return -1 because there's no second smallest value. Finally, to determine the result, we convert the set into a sorted list. The smallest value will be at index 0, and if a second element exists at index 1, we return it as the second smallest value. Otherwise, we return -1. To clarify this process, let's walk through an example. Consider a binary tree where the root value is 2, and its left child is also 2, while the right child is 5. The right child, in turn, has children with values 5 and 7. We first initialize an empty set. As we traverse the tree, we add the values 2, 5, and 7 to the set, resulting in a set of unique values 2, 5, 7. After traversal, we convert the set into a sorted list 2, 5, 7. The second smallest value, located at index 1, is 5, which becomes our output. Contrast this with a tree where all nodes have the same value, such as 2. In this case, the set of unique values remains 2, and the sorted list is simply 2. Since there's no second element, the output is -1. The use of a set is critical to this algorithm because it eliminates duplicates automatically, making it easier to collect only distinct values. Sorting the set after traversal allows us to directly access the smallest and second smallest values, with the sorting operation taking O, k log k, time, where k is the number of unique values. Regarding tree traversal, both BFS and DFS are efficient, as they visit each node exactly once, yielding a time complexity of O, n, where n represents the total number of nodes. Together, these steps ensure the algorithm processes the tree in a structured and efficient manner. Additionally, we use a queue for BFS or a stack for DFS to manage nodes during traversal, ensuring all nodes are visited in the correct order. Now, let's analyze the complexity of the algorithm. The overall time complexity is O, n plus k log k. The O, n, term comes from traversing all n nodes of the tree, while the O, k log k, term comes from sorting the k unique values collected in the set. For space complexity, the set used to store unique values requires O, k, space, where k is the number of distinct values. The queue or stack used for traversal requires O, h, space, where h is the height of the tree. Thus, the overall space complexity is O, k plus h. It's also important to consider edge cases. For instance, if the tree is empty, we immediately return -1. Similarly, if the tree contains only one unique value, we return -1 since no second smallest value exists. Finally, even for trees with large values, Python's handling of integers prevents overflow issues, though this might need attention in other programming languages. To implement the algorithm, we initialize an empty set to store unique values and use a queue for BFS traversal. Starting with the root node, we process each node in the queue by adding its value to the set. If the node has left and right children, we enqueue them for further processing. Once all nodes have been traversed, we convert the set into a sorted list to access the smallest and second smallest values. If the sorted list contains at least 2 elements, we return the second smallest value at index 1. Otherwise, we return -1. This simple yet efficient approach ensures that we handle all edge cases, traverse the tree completely, and return the correct result in all scenarios. This Python implementation solves LeetCode problem number 671, second minimum node in a binary tree. The goal is to find the second smallest unique value in a binary tree. If all nodes have the same value or there is no second smallest value, the function returns -1. The find second minimum value function is implemented as part of the solution class. The function begins by defining a helper function DFS, depth first search, that traverses the binary tree recursively. This helper function takes a node as input and adds its value to a set called unique_values. The recursive traversal ensures that all nodes in the tree are visited, and the unique_values set captures all distinct values. After the traversal, the code checks if the number of unique values is less than 2. If so, it means there is no second distinct value, and the function returns -1. Otherwise, the smallest value in the set is identified and removed. The second smallest value is then determined by finding the minimum of the remaining values in the unique_values set. This implementation is efficient because it uses a set to collect unique values while traversing the tree only once. The time complexity of the solution is O, n, where n is the number of nodes in the binary tree, as each node is visited exactly once. The space complexity is O, h plus u, where h is the height of the tree, for the recursion stack, and u is the number of unique values in the tree. This approach handles edge cases such as 1. A tree with only one node, returns -1. 2. A tree where all nodes have the same value, returns -1. 3. A tree with exactly 2 unique values, returns the second smallest. The code is structured, concise, and avoids unnecessary computations, making it a clean and effective solution for the problem. Here, we begin by importing the necessary classes and defining our solution class. The main method, find second minimum value, takes the root of a binary tree as input and aims to find the second smallest value in the tree. To accomplish this, we use a hash set called unique values to store all the distinct values encountered in the tree. Then, we call a helper function, traverseTree, which performs a depth-first traversal of the binary tree to collect these unique values. Once the traversal is complete, we check if the size of the set is less than 2. If so, it means there aren't enough unique values to find a second minimum, so we return -1. Otherwise, we find the smallest value in the set using collections.min, remove it, and then find the smallest value again in the updated set. This second minimum value is returned as the result. The traverse tree helper method is where the recursive traversal of the binary tree happens. If the current node is null, the function simply returns, ensuring we don't attempt to process non-existent nodes. Otherwise, we add the value of the current node to the unique values set, guaranteeing that only distinct values are stored. Next, the method recursively calls itself for the left and right child nodes, enabling a complete traversal of the tree. At the bottom of the slide, we also have the treeNode class defined. This class represents the structure of a binary tree node, with its value, a left child, and a right child. It includes constructors to initialize the node with just its value or with both its value and child nodes. This structure forms the backbone for our solution, allowing us to navigate and process the binary tree seamlessly. Here we have our first example, which is a simple binary tree with two unique values. The root node has a value of 2, with a left child also having the value 2, and a right child with the value 5. To find the second minimum value, we start by initializing an empty set called unique_values to store all distinct values encountered during the traversal. We then begin a depth-first search, starting from the root node. The value of the root node, 2, is added to the set, so now unique_values contains just 2. Next, we move to the left child of the root, which also has a value of 2. Since 2 is already in the set, there's no change. The left and right children of this node are both null, so we return back. Then, we examine the right child of the root, which has a value of 5. This value is added to our set, resulting in unique_values equals 2, 5. The left and right children of this node are null as well, so the traversal is complete. At the end of the traversal, our set contains the values 2 and 5. Since the set has more than one element, we remove the smallest value, which is 2, leaving us with unique_values equals 5. Now, we find the smallest value remaining in the set, which is 5, and return it as the second minimum value. Therefore, the output for this example is 5. In the next example, we have a binary tree where all the nodes have the same value. The root node and both its children all have the value 2. We begin again by initializing an empty set unique_values and starting the depth-first search from the root. The value of the root node, 2, is added to the set, so now unique_values equals 2. Next, we move to the left child, which also has the value 2. Since this value is already in the set, no change occurs. The left and right children of this node are null, so we return to the parent node. Then, we examine the right child of the root, which also has the value 2. Again, since this value is already in the set, no change is made. Continuing the traversal, the left and right children of this right child are null as well, so we return to the root. At the end of the traversal, our set still contains just one value, unique_values equals 2. Because there is only one unique value in the tree, it means there is no second minimum value. As the problem specifies, in cases like this, we should return -1. Therefore, the output for this example is -1. Now, let's move on to a larger binary tree that contains multiple unique values. The tree has a root value of 2, with a left child also having the value 2, and a right child with the value 5. This right child has two children of its own, the left child has a value of 5, and the right child has a value of 7. We start by initializing an empty set unique_values and begin our depth-first search from the root. The value of the root node, 2, is added to the set, so now unique_values equals 2. Moving to the left child, which also has the value 2, we add it to the set, but since it's already present, there's no change. The left and right children of this node are null, so we return to the root. Now, we examine the right child of the root, which has the value 5. Adding this value to the set results in unique_values equals 2, 5. The left child of this node also has the value 5, so adding it doesn't change the set. The left and right children of this node are null, so we move to the right child of the node with value 5, which has the value 7. Adding this value updates the set to unique_values equals 2, 5, 7. Both children of this node are null, so the traversal is complete. After traversing the entire tree, we remove the smallest value, which is 2, leaving us with unique underscore values equals 5, 7. The smallest value remaining in the set is 5, so we return it as the second minimum value. The output for this example is 5. To understand the time complexity of this solution, we start with the depth-first search, or DFS, traversal of the binary tree. In the DFS function, we visit each node exactly once. This ensures that for a tree with n nodes, the traversal itself takes n time. Now, as we traverse, we insert each node's value into a set called unique underscore values. Adding an element to a set is an average O(1) operation, so for n nodes, these insertions collectively also contribute n time. Once the traversal is complete, we perform some set operations, such as finding the minimum value and removing it. These operations depend on the size of the set, which is k, the number of unique values. In the worst case, when all nodes have unique values, this is still bounded by n. Therefore, when we combine the DFS traversal and the set operations, the overall time complexity of the solution remains n. Now, let's analyze the space complexity. First, consider the recursive call stack used during the DFS traversal. The depth of this stack depends on the height of the tree. If the tree is unbalanced, the height could be as large as n, leading to an n space requirement. On the other hand, if the tree is balanced, the height is log n, which significantly reduces the space used by the stack. Next, we have the unique underscore values set, which stores all the distinct values encountered in the tree. In the worst case, where each of the n nodes contains a unique value, the set would require n space. Combining these two factors, the total space complexity in the worst case is n, dominated by the larger of the recursive stack or the set storage. When comparing this optimized approach to a brute force method, the advantages become clear. A naive solution might involve collecting all the node values in a list, sorting the list, and then finding the second smallest value. While functional, this approach requires sorting, which has a time complexity of n log n, making it less efficient than the n time complexity of the set-based approach. The optimized solution avoids unnecessary sorting by leveraging the properties of sets for quick insertions and lookups. Looking at best, average, and worst-case scenarios, the time complexity remains n in all cases, since every node is visited exactly once. Space complexity, however, varies. In the best case, where the tree is balanced and there are few unique values, the space requirement is minimal. In the worst case, with an unbalanced tree and all unique values, space complexity reaches n, primarily due to the stack depth and the space used by the set. To mathematically confirm these complexities, we can break down the operations. The DFS traversal guarantees that each node is visited exactly once, contributing n to the time complexity. Set operations, including insertion, lookup, and removal, are O(1) on average for each node, so for n nodes, set operations also total n. Altogether, the time complexity is n. On the space side, the set used for storing unique values requires space proportional to the number of unique values, which is at most n. Meanwhile, the recursive call stack space usage depends on the tree height, which is n in the worst case. Thus, the overall space complexity remains n, combining both the set storage and the call stack depth. When solving this problem, there are a few common mistakes to avoid. The first is not handling duplicates properly. Some trees may contain repeated values, and if you assume all values are unique, you might end up returning the smallest value instead of the second smallest. To fix this, you can use a set or another data structure to collect only unique values before processing. Another issue is inefficient traversal. For example, visiting every node even after you've identified the necessary values can unnecessarily increase the time complexity. Instead, you should aim for early exits or targeted traversal techniques, like using depth-first or breadth-first search with specific conditions. Lastly, assuming the tree is a binary search tree can lead to incorrect logic, such as relying on in-order traversal properties. Always ensure you carefully read the problem constraints to understand the type of tree you're working with and avoid making such assumptions. Another common pitfall is incorrect sorting logic. For example, some solutions sort the entire list of values when you only need to track the two smallest ones. This adds unnecessary computational overhead. Instead, you can use a linear scan to directly find the smallest and second smallest values, which is much more efficient. Additionally, it's easy to overlook edge cases, such as trees with only one unique value, empty trees, or trees with just a single node. To address this, make sure you include thorough edge case testing in your implementation. Identifying these scenarios early can save significant debugging time and ensure your solution is robust. Understanding some key insights can help you perform better in interviews involving tree problems. Recognizing traversal patterns is crucial, as many tree-based problems depend on techniques like depth-first or breadth-first search. For instance, depth-first search is often useful when you need early exits. Be ready for follow-up questions, such as variations that involve finding the kth smallest value or handling additional constraints like time or memory limits. Another area interviewers often focus on is time complexity. They typically expect solutions with linear time complexity, so avoid approaches that rely on sorting unless explicitly required. Lastly, discussing edge cases with your interviewer before starting to code demonstrates thoroughness and can prevent unnecessary issues during implementation. Related problems you can practice include finding the kth smallest element in a binary search tree, performing level-order traversal, and determining the maximum depth of a binary tree. There are several approaches to solving this problem, each with its own trade-offs. A brute force method involves collecting all unique values into a set and then sorting them to find the second smallest. While this is simple to implement, it has a time complexity of n log n, making it inefficient for larger trees. A more optimal approach is the linear scan, where you traverse the tree once and dynamically track the smallest and second smallest values. This has a time complexity of n, but requires careful handling of duplicates and edge cases. Alternatively, you could use a priority queue or min heap to maintain the two smallest values. This method can be useful for kth smallest problems but is generally overkill for just the second smallest. Lastly, a recursive approach with depth-first search allows you to maintain state for the smallest and second smallest values. This method is elegant and memory efficient but may be harder to debug compared to iterative solutions. Each approach has its strengths, so choose based on the problem constraints and your familiarity with the techniques. Great job following along. In this session, we tackled an important tree traversal problem and discussed how to find the second smallest value in a binary tree. By understanding the brute force approach, we set a foundation for exploring optimized solutions. Thanks for watching, and see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!